end of this video, you should be able to describe what's meant by nuclear fission and a chain reaction. You should then be able to describe how nuclear fission may be controlled or uncontrolled. And finally, you should be able to describe what happens in nuclear fusion. And all of this is for triple physics students only. So we're going to start by looking at nuclear fission. The first key idea you need to understand is that in some elements, the nucleus is large and unstable. And good examples of these are uranium and plutonium. Now, I should point out that this only applies to certain isotopes of these elements, but for the exam, you're not required to name those isotopes. In nuclear fission, the nucleus of these elements splits. Now, this can happen spontaneously, in other words by itself, but that's quite rare. Normally, for fission to take place, the nucleus first has to absorb a neutron. So, here I'm showing you a number of uranium nuclei. When a uranium nucleus absorbs a neutron, this triggers the nucleus to undergo fission, in other words split, like this. When the nucleus splits, it forms two smaller nuclei, roughly equal in size. Scientists call these the daughter nuclei. It also emits 2 or 3 neutrons plus gamma radiation. Energy is also released during the fission reaction. For example, all of the fission products have got kinetic energy. Now, the really important part about this process is what happens to the neutrons emitted during fission. The neutrons can now be absorbed by more uranium nuclei and trigger fission again, like this. And again, when these nuclei undergo fission, they emit 2 or 3 more neutrons each, and these can then go on to trigger fission themselves. So in a very short time, a huge number of uranium nuclei have undergone fission, and an enormous amount of energy has been released. Scientists call this a chain reaction, and it's really important that you learn that. Now, scientists can control the fission chain reaction and use the energy released to generate electricity. We find this in nuclear reactors. However, the explosion in a nuclear weapon is caused by an uncontrolled fission chain reaction. Okay, so we've seen what happens in nuclear fission, but what about nuclear fusion? This is a totally different process. In nuclear fusion, 2 light nuclei, for example hydrogen, are joined to form a heavier nucleus. Some of the mass of the nuclei can be converted into energy, and that's released as radiation. Now, nuclear fusion is the process that releases energy in stars, such as the Sun. It's important to understand that nuclear fusion is not a chain reaction. We only use that expression when talking about nuclear fission. Remember that you'll find plenty of questions on nuclear fission and on nuclear fusion in my Revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe what's meant by nuclear fission and a chain reaction. You should then be able to describe how nuclear fission may be controlled or uncontrolled. And finally, you should be able to describe what happens in nuclear fusion.
The famous equation E equals mc squared tells us that the energy of a particle is proportional to its mass. So, if we wish to create mass, we could imagine having its energy would allow for this. But it turns out that twice the energy is needed. For what I want to get into, we need a short detour here into pair production and annihilation. That's because we need to produce not only a particle, but its antiparticle. Electrons have an antimatter particle called the positron, almost identical to each other, but with an opposite charge. What this means is that they act oppositely in electric and magnetic fields. Shown is a cloud chamber. The inside is saturated with water vapor, and if a charged particle moves through it, it will leave a track behind her as water droplets form. What the scientists did was applying magnetic field, so a moving charged particle would want to move in a circle, the size of which is related to their mass. The purpose of this is that different charges move in different orientations around a circle. For example, a positive charge might go clockwise, whereas a negative charge will go anti-clockwise. What Cody Anderson found was a positive charge in cosmic rays, not unusual as both protons and alpha particles are positively charged. However, he found the mass of the particle to be significantly less than that of a proton. It was at most twice the mass of an electron. This figure from 1932, winning the Nobel Prize for Physics in 1936, shows the positron as the long line through the middle. Today, with better detectors as well as the ability to create pair production on demand, we have much better figures demonstrating pair production. For example, this one was taken from the Aleph detector at CERN, showing pair production of electrons-positrons. The reaction that causes an electron-positron pair is a photon splitting into an electron and an anti-electron. The energy of the photon has to be enough to create both of the particles. Now into the meat of the video. What the equation E equals mc squared does is relate mass to energy. That is, if we had some mass, and if it was all changed to energy, this is how much energy we should get. For example, if you could turn a kilogram of mass, about 1 litre of water, into pure energy, how much energy would you get? The speed of light is exactly 299,792,458 meters a second. So the square of the speed of light is about 9 followed by 16 zeros. As we had 1 kilogram, that means we get 9 followed by 16 zeros joules of energy. These numbers are kind of meaningless without an example. So let's consider Fat Man, the bomb that was dropped on Nagasaki. It had about 9 trillion joules, about 9 followed by 12 zeros. So we need 10,000 of them to match 1 litre bottle of water. However, to change a litre of water to energy, you will need a litre of anti-water, which is rather hard to find. So you may be wondering what's the point of the equation E equals mc squared? How could we possibly use this concept? To do so, I'm going to have to make a few things clear. Because of the equation, we can talk about mass in terms of energy, or energy in terms of mass. However, when we have a very, very small amount of energy, we need a better unit than a joule. To do this, we're going to have to define a new measure of energy. So, we define an electron volt to be the energy an electron gets when it is accelerated through 1 volt of potential difference. This is a very useful unit as it's about the energy scale of the mass of particles. A mega electron volt is 1,000,000 electron volts. So let's now look at the mass of some particles. The mass of an electron is 0.51 mega electron volts. The mass of a proton, 938.3 mega electron volts. A neutron has mass 939.6 mega electron volts. And the deuterium nucleus has a mass of 1875.8 mega electron volts. Now a deuterium is made up of a proton and a neutron that have been bound together. So if we add the mass of a proton to the mass of a neutron, we find that the total mass is 1877.9 mega electron volts. However, the mass of a deuterium, like I just said, is 1875.8. Why is deuterium lighter? 2.1 mega electron volts is quite a substantial amount. Like I said, an electron has mass 0.511 mega electron volts. The reason deuterium is lighter than the sum of its parts is that when a neutron and proton bind together to form a deuterium, it loses some mass. But what do I mean by loss of mass? Remember that mass and energy are equivalent. So what I'm actually saying is a loss of energy. And so we introduce the concept of binding energy. That the bound system can have a different energy than the sum of its component parts due to the interaction of the parts. For example, if you push together 2 of the same poles on a magnet, or if you push together opposite poles, the energy is different. If a system had a state of lower energy, once in that state, energy would need to be added in order to put it back into its original state. But as the system goes into a lower state, by conservation of energy, the difference of energy has to come from somewhere. So the mass decreases in order to compensate, again by E equals mc squared. In order to separate the system back to its component parts, the same amount of energy will need to be put back into the system. This process is the basis of how nuclear fusion and fission both work. Fusion is when we push together atoms, protons and neutrons for example, forming a new atom. Like we have just shown, a proton and a neutron binding together to form a deuterium. We could also fuse the deuterium nuclei together to form a helium nuclei, each releasing energy when the particles get fused. However, as we fuse more and more
particles together, the amount of energy released decreases. However, the binding energy is still increasing, up to a point. Once past this point, the binding energy decreases. Once the binding energy for lighter elements becomes higher than that for heavy. If we separate the heavy elements, we get energy released, as the system is now going to a state of higher binding energy.
This is the process of nuclear fission. Note that both of these processes can happen at any binding energy, except you only get energy released when you go into a higher binding energy. For an example of a fission reaction, uranium-238 fissions into an alpha particle and thorium-234.
By a similar concept, if we look back at the mass difference between a proton and a neutron has more energy than a proton, it has a higher mass. So neutrons are able to decay into a proton. This is via the reaction of a neutron changing into a proton, an electron, and an anti-electron neutrino. This is a process of a decay of a free neutron. That is, when the neutron isn't caught up in an atom. Neutrons have a half-life of about 15 minutes. That is, given a very large number of neutrons, after 15 minutes, you expect half of them to be gone. If you have a single neutron, after 15 minutes there is a 50% chance for it to have changed into a proton. More accurately, the wave function of the neutron has changed into a superposition of both, each with probability a half.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So, a nuclear reactor successfully generates nuclear energy from fission reaction.